Today we consider Rlc circuit. In the last class we considered the Rlc circuit under driving force, that is alternating current. And we learned that the output voltage of the resistor becomes maximum at omega driving. Omega D reaches resonance frequency, and that resonance frequency was omega 0, that is 1 over square root LC, or LC oscillator. Today we consider the phase difference in each component, each circuit unit of Rlc circuit under the application of the alternating current. The potential applied to a resistor, if you follow the direction of current, this VA and VB equals VA minus IR. The potential decreases as we cross the resistor, and we define VR of T by eliminating negative sign. We know the potential decreases, so IR. And to identify it is passing the resistor, we put subscript R. So something like Ohm's law, VR equals R IR T. Because this is a real number, this and this, they have the same functional dependence except for the amplitude. If we apply the potential, this potential, to be VR of T equals amplitude VR sine omega dt, then it has a period T, that T equals 2 pi over omega driving force. Because of this relation, here this is a VR sine omega dt, IRT is completely determined. That is VR over R VRT, IRT equals. So IRT has sign dependence. VR over R sine omega dt. and IR's amplitude is determined as I. So this is IR sine omega dt. Therefore, we obtain this result. The amplitude of V is VR, amplitude of current, VR over R. If we compare this one, this is IR. So we rewrite this one, VR equals R times IR. It's something like Ohm, this is Ohm's law. In addition, we have a complete the functional dependence is completely the same. We have sine function for the potential and exactly the same sine function for the current. So we current and potential, they are in phase. For resistor, current and potential are completely in phase. Next, we consider the case of capacitor. Capacitor we have current I is coming in. Then we have charge Q of C capacitor. And the other side, it becomes a minus Q of C T. And current flows out. The potential difference from here to there, VA and VB, then VB equals VA minus QC over T over C. So this potential is lower than this. We define VC to be the positive value, this one, we define this one by VC of T. When the potential is given in this form, and this potential has amplitude VC, capital VC, and sine omega dt. If it is the case, if we multiply charge C, then Q C of T equals CVC sine omega dt. The charge and potential, they are in phase. And the amplitude, this is for Q of C. Once we know the charge, I can compute IC of T by taking the time derivative of QC. If I take the time derivative of QC, we have omega d CVC, and sine becomes times cosine omega dt. Because of this, I can determine the current to be omega dc vc and cosine omega. And cosine x can be expressed in terms of sine x plus 1/2 pi. Sine addition formula is sine x cosine half of pi plus cosine x sine half of pi. Cosine 1/2 pi is 0 and sine half of pi equals 1. Therefore, it is cosine x. So cosine x can be expressed in terms of sine x plus 1/2 pi. So this cosine omega dt can be expressed as a sine omega dt plus 1/2 pi. Suppose that you have a function y equals x f of x plus a. This is related to y equals f of x by translating. This is f of x, y, x, translating by minus a. Then this curve is like that. This is a. Translating by this direction, positive direction, this is minus a, this is plus a, then function becomes like that. And this function is fx plus a, and this function is fx minus a. Therefore, y f of x plus a is same as the y equal f of x, except that translate by minus a. So this one is the same as a sine x translate by minus 1/2 of pi. Let's see. This is the sine function. We c over t for amplitude sine omega dt. And we want to translate this function backward by 1/2 of pi. Backward. This peak is translated by 1/2 of pi. I mean, including omega dt. So, backward translation. This is cosine omega dt, and that is sine omega dt plus 1/2 of pi. So, plus 1/2 of pi says the current, phase of current is shifted. The graph is shifted by 90 degrees. This is potential. This is current. In addition, This IC is identical to this. This IC is omega C Vc. This amplitude relation, following the Ohm's law-like system, potential is reciprocal of this, 1 over omega c multiplied by the amplitude of current. So V equals Ri for resistor, but for a capacitor, it is not this, but 1 over omega dc. So this one behaves like the resistance of the resistor when alternating current is applied. And the current is behind the potential by 90 degrees. It is shifted backward, shifted in comparison with the potential. Current is backward, shifted backward by 90 degrees. Next, we consider inductive load. An inductor that has the inductance L, if current I is flowing in the direction of a current, the potential difference is a minus L di over dt. We denote VL by the positive value L di over dt, where IL is the current passing through the inductor. If we consider the sinusoidal wave, the potential difference is like that. That means amplitude for the potential multiplied by sine omega t. Because it is proportional to the time derivative, if we integrate this potential, what we obtain is a current. If we integrate this, neglecting the constant term, integrate, then sine integration of sine, so I mean IL t equals 1 over L VL t dt, and VL dt is substituted in here, so VL over L integral. Integral of sine omega d t dt. That is a minus omega d L VL cosine omega dt. So this is written in here. Here, as we have done with the capacitance, minus cosine omega dt, that is minus cosine x. Actually, that is sine x minus half of delta, half of pi. Let's see. That is a sine x cosine minus half of pi, cosine x sine minus half of pi. This one is 0, and this one is minus 1. Therefore, we have minus cosine x. Therefore, minus cosine omega dt is replaced with sine omega dt minus half of pi. Here IL is VL over omega dL. And here. The amplitude relation for the potential, amplitude for the potential is now omega dL multiplied by the amplitude of the inductor. The time dependence of potential this one oscillates and ILT, so IL sine omega dt minus 1/2 of pi. That means shift this figure by this one is half of pi. Shift this, so this point is shifted in here. By this figure is shifted by half of pi. If we replace with the omega dt, this omega t. As a result, the current of the inductor is 90 degrees in radian is half a pi ahead of VL. 90 degrees ahead of VL. Until now, we have considered this phase consideration using real variable real analysis. But if we introduce complex variable, these analyses can be analyzed with ease. Complex number is a solution of quadratic equation. And the general solution for this quadratic equation is complex number. Complex number is a linear combination of 1 and pure imaginary number multiplied by real numbers and sum. So these two are real, and we call this one as a Z. And I is the solution of this quadratic equation. So there are two solutions, plus minus square root minus 1. We call I to be square root minus 1. Okay. Then we define the addition of two complex numbers, x1 plus iy1, x2 plus iy2, sum of them, and this is a real part, plus I y1 plus y2. That is imaginary part. Real part, and imaginary part. Multiplication of two complex numbers x1 plus iy1, x2 plus iy2. Real part is real, x1, x2. Imaginary, there's y1, y2, but I square is minus 1. And the cross term, x1, y2, and y1, x2. This is the way of multiplying two complex numbers. We have x plus iy as a complex number z, and complex conjugate z star is defined by this. The imaginary part is flipped. If we multiply two numbers that are complex conjugate, x plus iy, x minus iy, that is x squared minus iy squared, that is x squared plus y squared. And we call the square root of this real part square and the imaginary part square, that is called modulus. The modulus. And this is a modulus square. A complex number z equals x plus iy can be matched to this is iy, a coordinate, two-dimensional Euclidean space. So using Cartesian coordinate, we can introduce the polar angle theta to represent x equals r cosine theta and y equals r sine theta. So if we add these two, z equals x plus iy equals r cosine theta plus I sine theta. We define this number that whose modulus is 1. This is e to the I theta. So this polar coordinate representation of the complex number is very convenient for our calculation. If we substitute theta equals 0, then we have e to the I theta equals cosine 0 plus I sine 0. That is 1 plus I 0, that is 1, when theta equals 0. If I take the derivative, cosine's derivative minus sine, sine's derivative of cosine. So, because this one is I squared, I can factor I out, and again we have e to the I theta. So I times e to the I theta. It is just like real variable function e to the ax. When we take the derivative with respect to x, then we have over a factor a with the same form. If we multiply two complex numbers, they can be expressed in terms of e to the I theta 1 and e to the I theta 2, R1 and R2. And we have the product of this modulus, and we are interested in computing the e to the I theta 1, e to the I theta 2. That one can be made this way. Real part is cos minus sin sin. Imaginary part cosine sine cosine. And this is cosine theta 1 theta 2. And this is sine theta 1 plus theta 2. Again, we return to the exponential form. That is exponential theta 1 plus theta 2. So if we multiply two complex numbers, the modulus is multiplied and argument is being added. If we divide two complex numbers, then we have this one, and we can multiply 1, that is a z2 star over z2 star. If we multiply these two numbers, this is the absolute value of z squared. And this is a product of z1 and complex conjugate of z2. So modulus is R1, R2, and denominator modulus only, R2 squared. Argument is theta 1, but this is complex conjugate. The argument is minus the theta 2. So the overall factor is the ratio of modulus, and the argument is the difference. We can compute the modulus of the sum. That is g1 plus g2 and product of complex conjugate. If we expand, then z1 and z1 star gives z1 absolute value squared, z2, z2 star, z2 absolute value squared, z1, z2 star, and z2, z1 star. They are complex conjugate relatively. The absolute value of z1 and z2 product, and then this is a difference, theta 1 minus theta 2. The other one is a minus theta 1 minus theta 2. Because e to the I theta equals cosine plus I sine, e to the minus I theta equals cosine minus I sine. If we add these two, e to the I theta plus e to the minus I theta equals 2 cosine theta. So 2 cosine theta is factored out, and argument is difference. In general, exponential, a complex number, is sum of real number and complex number. Exponent can be separated, and this one gives a modulus and cosine y plus I sine y. Next, we consider phasor. We used to compute the sinusoidal function for the potential difference between the two terminals of a circuit element. But as we know, the current or charge, they are the solutions of the second order linear differential equation whose coefficients were all real. And we have seen that the corresponding complex function can be used to solve this problem. Then we replace this one with sine omega dt and another real solution for this, and combine them, add them up, and we have complex version, and then right side becomes A0 e to the I omega dt. So the solution of this can be found much easier than the sinusoidal function case, and then at the end of the day you will project out the real part from Z. In case you have a sine function, you take the imaginary part of Z to find out the particular solution. As I already stated, as t goes to infinity, among the general solution, only the particular solution survives, and the corresponding solution for the homogeneous equation completely disappears because the overall factor 1/2 gamma t. So we want to replace everything with a complex version. So amplitude can be a complex number, but the input EMF for the AC driving force is expressed in terms of exponential I omega dt instead of sine or cosine. Then everything else can be expressed in terms of a complex number in the polar coordinates. So for the time being, if we make use of complex version, we attach a superscript with C that represents a complex version. In the calculation, we need to find the derivative e I omega dt. Then we will find I omega d if we have integral neglecting the constant term, what we have something like that. So in comparison with treating sine or cosines, derivative integral has a simple calculation for multiplying I omega d or dividing the amplitude by I omega d. So the exponential, the computation using this exponential function is much easier, less confusing than using the sinusoidal function. If we have such an additional factor in the derivative, we face plus I as an additional factor. In the integral, time integral, we have 1 over I, that is minus I. This additional factor is because I absolute value equals 1, this is modulus 1. So this one can always expressed in terms of exponential I something. Exponential I something, a real number. This is half of pi, and this is minus half of pi. We know this is a unit circle of radius, unit radius, on a complex plane. Here, this is I, and this is minus I. Any complex number on a unit circle, z equals r e to the I theta, r equals 1, then z equals e to the I theta. And this is the angle, the right angle. I and minus I is e to the I right angle, e to the minus I right angle. Okay? So, using this fact, plus minus I is exponential plus minus I right angle. If we add this or multiply this, multiply it to the plus minus I to e to the I omega dt, then you are multiplying plus minus I half of pi I omega dt. And exponents can be added. So, treatment of phase shift calculation becomes trivial. So this is the reason why we use this complex number, and using complex number in the polar coordinates, r e to the I theta style, is called a phasor. So we prefer phasor to the sinusoidal function calculation. So let us return to the previous case. Resistive load we had in phase. Why? Because V of R of T, R, I of R of T, they are multiplied by a real number. A complex number Z equals R e to the I theta, but it becomes capital R is real. That means no phase. So we are, as far as the resistance is concerned, the current and potential, they are completely in phase. Because of that, the amplitude of in our convention, we use I, R instead of I. So this was our previous calculation, but if we use a phasor, it is a complex number that rotates depending on time with a fixed frequency, angular frequency, depending on the AC current. VR, the superscript C is complex number. So amplitude multiplied by the sinusoidal function. Sinusoidal function is replaced with I omega dt. For simplicity, to avoid any confusion, we use the convention to use e to the I omega dt for potential. And then compare the current with the potential. The current, because because of because of this, amplitude is completely determined with as an Ohm's law, and the time-dependent part is completely in phase. There is no overall vector containing e to the I theta that changes the phase. So for the resistive load, there is no phase difference between the potential and current. They are rotating with the same polar angle. Next, we consider capacitor by making use of the phasor. AC input of potential is attached to the capacitor. This is E minus QC T over C equals 0 is the circuit equation. And that is equivalent to this. And we name this one as a VCT. And we want to find the relationship between VCT and ICT. And QC of T equals C VCT, and ICT equals QCT's time derivative, that is a C VCT's time derivative. And VCT is e to the I omega dt, and with the amplitude, what we obtain is substitute this here. What we obtain is CVC I omega I omega d CVC e to the I omega dt. This is V, and this is current I. So current I has this form. The relationship between I and V sub C can be used. We write VCT, so this is a complex number. We end up with this relation. So amplitude relation is I C equals minus I omega dc because this is Vc of t equals Vc e to the I omega dt. The absolute value is the amplitude. Amplitude is Vc. And right side, absolute value is 1 over omega dc and amplitude. This one. This is Ohm's law-like relation. In addition, V equals something I, and something has minus I over omega c. So minus I is a number that can be expressed as I 1/2 pi. Therefore, potential is this one is e to the I omega dt, and this one is e to the I omega dt plus 1/2 of pi. In order to cancel this one, to have the left hand side equal to the left hand side. So current has a plus 1/2 of pi. Current has a plus 1/2 of pi. Is this angle is ahead. The current is by 1/2 of pi ahead of Vc. This one is e to the I omega dt, and this one is e to the I omega dt plus 1/2 of pi. Okay, before going ahead, let me correct some confusing remark in the previous discussion. The phase of IC is behind that of VC if we consider the graph itself. The graph is translated behind. But this is a little bit confusing, but usually they say is ahead of or leads. The reason is that because of the translation of the graph, actually this part has already passed. That means in the viewpoint of time, this amount has happened already. That means the phase is ahead. So please correct this part. I see graph is translated behind. That means in this graph at t equals 0, this amount has passed already in comparison with this sine wave. So we say this amount has passed already. That means the phase of current for the capacitor is advanced. It is ahead of the potential. The same is true that the graph in here is translated forward. That means this is 0, so this is not ahead, is behind. Because this graph hasn't translated forward, so we need this amount of time wait to happen to see what happens at the same phase up here. So we need additional amount of time to arrive here. That means it delays. So it is IL is behind of VL. Okay? At t equals 0, this 0 happens. At t equals omega 0, t equals half of pi, this one, the same event happens. All right? Therefore, IC is in this, if we make use of phasor, IC leads by 90 degrees. Let's see. IC leads ahead of. In the case of inductor, we have the potential is L times time derivative of current. And this VL is a reference. So we use WDT for VL. And this one, current can be obtained by integration. So VL over L integral. dt is missing. Alright. Therefore, we see from here, in comparison with VL, the VL is here, so this is VL. In comparison with VL, ILC VLT, let me do not write down, see that is IL. So over factor is minus omega d L. And we are interested in the expression VL equals something. So VL equals I omega d L I L. And VL has capital VL e to the I omega dt. This is I omega dt dl times IL. IL is proportional to e to the I omega dt. Therefore, IL this one is also IL. This one is also IL. Okay? So IL must be ILG must be IL e to the I omega dt, because we have to cancel this one minus alpha pi. So IL is behind VL, this phasor, by alpha pi, 90 degrees. Reactance. Now we have reached the point, the V equals IR style expression for the alternating current. For resistor, because the R is real, it is simple. V equals IR. Capacitor, we have a relationship in this form. We have a phase difference that has been considered already. As far as the amplitude is concerned, its amplitude is Vc, and whole amplitude is omega dc and Ic. These are real numbers. Therefore, this guy behaves like the resistance, but it is not actually the resistance, but we say the reactance. So reactance for the capacitive load is 1 over omega dc. In a similar manner, we had the factor of I omega dl. At the amplitude level, the amplitude is VL. This amplitude, the whole amplitude is IL and omega dl. I is this I, absolute value of I is 1. So omega dl is the reactance for the inductance. Reactance for the inductance increases proportional to omega d. For capacitor is proportional to 1 over omega d. That's quite important. So Ohm's law-like relation, V equals resistance times current for the resistor. But if we apply the alternating current, resistor is the same. Capacitor, capacitive reactance is 1 over omega dc, and inductive reactance omega dl should be multiplied. Series of Rlc circuit. We obtain all of the partial results, and let's see what happens if we combine everything together. EMF alone, potential difference E, if we follow the current, choose the direction of current, here, from here to there, we have E. Here, we have E minus Ri. Here, E minus Ri minus L di over dt. And then here, we return to the same position. Equals 0. This gives this relation. Now, we substitute E of t, alternating current, either sine omega dt or cosine. But we had better use a complex number to simplify our analysis. This is a complex version. Again, the coefficients L, R, and C are real, so we can solve the problem in terms of complex numbers. And then finally, in case we have sine omega dt, we take the imaginary part. In case we have em cosine omega dt, then we take the real part of the complex solution. Again, as t goes to infinity, the contribution coming from the homogeneous equation disappears because it is proportional to 1/2 gamma t. So we only consider the particular solution. So a particular solution can be obtained by substituting this trial solution. Substituting this trial solution and dividing the over scaling factor e to the I omega dt, then amplitude relation becomes double time derivative minus omega d squared plus single time derivative I omega dr, and then plus c no derivative, and a0 equals en. This factor e to the I omega dt has been divided both sides. Now, a0 okay, and the solution, because the a0 is found, the solution can be obtained by attaching this one, this time-dependent factor. Once q is obtained, time derivative, so I omega d is multiplied and this same factor appears. So we multiply in the numerator and denominator, and this numerator becomes em, and the omega, this I omega d cancels this, so r survives, and the remaining part is expressed like that. We see this is r plus I omega dl, means inductive reactance subtracted by 1 over omega dc. That is a capacitance in reactance of the capacitor. So this is a complex number. So it's better to make it real, that is to multiply okay, and actually this one numerator can further be simplified as a square root of this. And this is e to the minus I phi. So we see if we define impedance, this is just z e to the minus I phi, where phi, tangent phi, is xl minus xc over r. Okay? So inductive reactance, capacitive reactance, the difference is added to have a complex number to find the complex phase phi. Using this relation, we end up with cosine, sine, and tangent. So we learned that resistance, inductive reactance, capacitive reactance, and when they are combined all together, then we have impedance. And there is a phase shift phi that is completely determined by this complex number. So phase constant phi is defined by this. The detailed calculation is given in here, so you can follow the practice solution for the combination of some part. For example, in RLC, just combine R and C, combine R and L, and combine L and C to see what happens. These are good exercise. And we again return to the resonance, and using the concept of impedance and reactance, inductive reactance, capacitive reactance, and impedance, we can compute the potential and power of the system. And in the previous class, we have seen V of R. V of R is maximized at omega driving is omega resonance, and at that time it is omega 0. And when we vary omega d, there is a sharp peak at omega 0, and the width of this peak becomes more sharper and sharper for smaller gamma. This reaches 0, this peak goes to infinity. Power in alternating current. Using this information, we can compute the power spent by the resistor. That involves the integral, average time integral of sine squared. When you average sine squared function, average over period, this is just 1/2. Because of this factor 1/2, this 1/2 can be divided into the amplitude. For example, sine omega dt. Then because later we squared this at average, v squared sine squared, and this is 1/2 v squared. This is number, so 1/2 v. So it's v squared. It's better to include this factor of 1/2 into the amplitude. So the amplitude multiplied by square root to 1 over square root to 2 is called RMS, root mean squared. So RMS is very convenient for the time averaging the power applied by alternating current. For example, current RMS amplitude can be used to find the current of the system, can be computed by the ratio of the potential, the total potential for the EMF RMS, divided by the impedance. Power spent by the resistor is I times R, and in here this I is the current that has been computed using this impedance. Substituting this current amplitude, so ERMS is here, we will find there is a cosine phi R over Z. If there is a current attached to only a resistor, then power should have been EI, that's it. However, if it is attached to RLC circuit, it is not the case, and there is a additional factor R over Z that is expressed as a cosine phi. This is called the power factor of the RLC circuit. And let me pass the transformer. You can follow details about in this notes regarding the transformer. Okay, that's it for today.